So today's video might be a little bit more rambly than usual, and that's because we're going to be taking a look at integrated circuits on Kicad, specifically some Kicad templates I'm releasing called ScottoModules. The first release of that is for STM32, but I do want to do like RP2040 down the road and maybe like some Atmega 32U4 stuff. For now, we're looking at STM32 because it's a really easy circuit to integrate. But with that said, I'm not an electrical engineer. I have tested these work on an actual board. They do work. Everything does function as expected, but there is probably room for improvement here. So if you do know more about PCB design, let me know down below what can change with these to make them a little bit better, especially for like future releases. Now, the final thing I do want to mention here before we dive in is that this video is sponsored by JLC PCB. They are my personal PCB manufacturer of choice I've been using for about the last year or so. They have really good prices and really good quality. And these modules are actually set up in such a way that they use JLC's parts library, so you don't have to worry about that when you're designing the board. You just export it and then upload to JLC. Everything will pre-populate. It'll be ready to go. So with that, let's jump in and we'll take a look. So first, we're going to go to my ScottoKeebs repo. I'll put it on the screen right now, and it's also in the description. We're going to simply click the code button here and download as a zip. If you do know how to use Git, you could also just clone this somewhere. So you can see that I have mine here. We have all our files inside here. We can go to the extras folder. We're going to go to ScottoModules, and then we'll see this folder for the STM32. You're going to want to take note of where this is stored on your computer because we're going to need to actually reference this inside of Kicad in just a moment. So if we jump into Kicad here, we can go to File, New Project from Template. We're going to go to the folder icon here. We're going to go back to that ScottoKeebs folder. We're going to go to Extras. We're going to go to ScottoModules and then click this STM32 folder right here. We'll click that. We'll go to the ScottoModules, which is right here, and you'll see some info about it. We'll press OK down below. And I'm just going to save this to my desktop as YouTube. We'll click save, and then we can just jump into the schematic. So we're going to look at the schematic first because this will give you a really high level understanding of how all this works. Then we'll take a look at the PCB editor to get an idea of how everything's routed. And then finally, we'll close up with looking at the actual physical PCB to give you an idea of what it looks like on a real PCB. So this is the schematic right here. And you can see that we have a really big layout right here. That's because this is where your matrix would typically go. This is the point where I want to recommend, if you haven't seen my previous video on how to actually use Kicad, if you don't know what a keyboard matrix is, go watch that before this one, because otherwise you're probably going to be really lost now. But with that said, what we're going to do is just zoom in, and we have two little modules here. We have our STM32 module on the left, and then we have our USB-C module on the right. What we're going to begin by looking at is our controller section, which this is just our MCU. So this is our STM32 F072 CBT6. There's a bunch of different types of STM controllers, but the F072 CBT6 one here, this seemed like the best one for this use. So what we're going to do here is just kind of run it down. Basically, first of all, we have our voltage pins up top here, just going to 3v3. On the bottom, we have our two ground pins. All of these on the side are GPIO, so these are all GPIO you can use. We will talk about F0 and F1 in a moment, but these are also GPIO over here. We have our data plus and minus, so these are what your USB will use. So when you route it to the actual USB port, we'll be sending these to it. And these here, these yellow ones, are actually what are known as a differential pair, because USB lines are known as what's called an impedance controlled line, meaning that they should be relatively the same distance from one another or the same length. So by defining these labels here, we basically allow them to be routed as a pair, which I'll show when we look on the actual PCB editor in a moment. But that's the basic rundown of the MCU. If we look up on the top here, we have this N reset pin. This is specifically for resetting the controller. You could put a button on this, but what I did here is I just put a capacitor here pulling it to ground. This is in the data sheet to kind of prevent like parasitic resets. So you use that capacitor to pull it down to ground here. And we're not using a button, but you could use a button if you wanted to. And then finally, what I want to talk about on here is the boot button. So this is for the boot global label. And if we come over here to the reset switch, I'm calling it the reset switch, even though it is a bootloader button. Basically, you hold this when plugging the board in, and it'll allow you to get into bootloader mode to flash your firmware. But you can see what we have is on one end of this switch here, we have our 3v3. We have our boot global label here, which is defining that this side of the switch will be connected to our controller right here. And then we just have a 10K resistor right here pulling it down to ground. That's part of the spec also for this, but that is our reset switch there. And that is our overall MCU. Now, the final thing on here I want to discuss are these F0 and F1 pins. These are GPIO. You can use these. But one really cool thing with STM32 in particular is that it has a built-in crystal or built-in clock, so you don't need an external crystal circuit. You could use these pins here though if you wanted a more accurate crystal, so you want to probably avoid these if you are going to be using them as GPIO, or use them last if you have to. But that's the basic layout of the MCU chip itself and the reset switch. What we're going to look at next are the decoupling capacitors down here. Now, decoupling capacitors are a little bit confusing at first. They're not exactly crucial for keyboards in particular from what I've seen on my research. They are still required, especially according to the data sheets. These do veer off a little bit from what the data sheet for the STM32 I'm using here does say. But basically what these decoupling capacitors here do is they filter out noise from your MCU. So any power pin is going to be producing some level of noise. I'll try to find some videos to link down below explaining this a little bit more. So what we have here is that we have 5 different ones and then a bulk on the end, and these assign to each power pin. So if I go up to the MCU here, what you can see is that we have our 5 pins for power. These are all 3v3. So we have, of course, 5 decoupling capacitors here, and then this final one that's a little bit bigger, which is just a bulk decoupling. Now, a bulk decoupling is just kind of like an overflow, how I think of it. I don't know if that's technically correct what it's doing, but it's like if everything else overflows, it overflows into that one to clean it up a little bit further. Technically, I think you need 7 according to the data sheet for the STM32, but I'm using this one here. It does work. It uses minimal parts and is a lot simpler to understand. But basically, we just have a bunch of capacitors here. One end is connecting to the 3v3 up top, and then down here is just going to ground. So pretty easy to understand there. So next, we're going to talk about the USB-C module, which is kind of handles everything from power regulation to ESD protection, and of course, connecting to the data lines. So if we come over here to our USB-C section, you can see that we first have our connector here. This here, of course, is the connector. And if we look up top, we have our V-bus line. Now, this is only specific to kind of PCB design. I don't know the exact specification of this, but basically, we all know that USB is actually 5 volts. So USB is 5 volt. Any type of USB connector is 5 volt typically. So we have that known as V-bus here, but V-bus is technically 5 volts. So we feed our V-bus in. We have a V-bus line just coming out here. We don't actually use this. And then we have a 500 milliamp fuse right here. And then you can see afterwards, it becomes 5 volt. So basically V-bus before the fuse and then 5 volt after the fuse. Now, that's our little fuse here. The reason we have that fuse also is that it basically protects if, say, you connected a hot USB somehow, it's going to prevent blowing up the rest of your circuit. So this fuse will actually pop and then protect the rest of your circuit. And it's also known as what's known as a resettable fuse, meaning that it will reset and kind of lose ability each time it does reset. So it's not like a car fuse where it pops and it's done and you need to replace it. It will reset, and then say if it pops at 60 volt the first time, maybe the next time it will pop at 58 volts or 57 volts. I believe I'm using a 60 volt fuse on here. I believe that's what the spec is for this one. But if we look down below here, we have our CC1 and CC2. I don't know specifically what these are. I just know they're part of the USB spec. We basically need to put a 5.1K resistor going to ground on these. So we have those pins just kind of grounding out right there. And then finally, we have our data minus and data plus lines. You can see that there are actually 4 pairs here. If I can select these right here, we have our 4 pairs of data plus and data minus. That's because USB-C is reversible. So if we put it this way, it's going to use one pair. If you put it that way, it's going to use the other pair. Simple as that. We're just kind of tying them together here, setting them to a global label for data plus and data minus. Now, the final thing on this, of course, is grounding. So if we come down here to grounding, we have our shield and our ground just both going to ground. Some people argue that you should actually ground out the shield separately from ground, but I'm just kind of tying these both together here and sending them to ground. I saw things that said that's fine, so that's what I'm doing. So the next thing to talk about here is ESD protection. So if we scroll over, we can see that we have our ESD protection little module right here. Basically, we're just feeding in the data plus and data minus lines right here. We're sending one end to ground, one end to 5 volt, and this is our actual ESD protection chip in the middle. Basically, what ESD protection does is it protects, like, if say you have static electricity on your hands and you touch the board, this chip's going to protect from that frying the rest of your circuit too. So we basically use this here along with the fuse to kind of protect the rest of our circuit. Now, the final thing I want to discuss here is the voltage step down, which this is particular to STM32, I believe also RP2040, because USB is 5 volt. We want to get it down to 3v3 volts. So as if we look over on our actual chip here, we have 3v3 volt. So that's not going to take 5 volt going in. So we're just using this XC6206 chip. We basically have V in here. So we have our 5 volt feeding into the V in. We have a 1 UF capacitor here. And we also have one on the other end on the V out. So we have a capacitor on both ends. So you can see V in, we have 5 volt, we have V out, comes to 3v3. And we have capacitors. Those are known as stabilizing capacitors. They basically just smooth out the current. But then we also just finally ground it out. And that's the basic schematic for a voltage step down. So that's the overall schematic. There really isn't much to this here. There's just these 5 or 6 little modules here. And technically it's actually, this is a module here and this is also a module. But I think that probably explains this pretty well to kind of give you a high level understanding of how the schematic works. What we're going to do now is jump into the PCB editor and kind of take a deeper look specifically with the routing, because this is where it can get a little bit more tricky because you have to kind of compact all these down. But what I did is kind of made them into modules so they're really easy to kind of like place where you want. So we're just going to jump into the PCB editor and take a look. So here we are inside of the PCB editor, and you see we have our left module here, which is the USB-C, and then we have our right module, which is the actual MCU. Now, the way these are actually designed to be used is really, really easy, is that if we actually just take the MCU module here and pull it down, you'll see that we want to connect our data lines. So we have our data minus and data plus right here. You can kind of see that. We have our voltage is expecting to connect to the voltage. And then we want to connect our reset switch, which will go to the pin over here. And then we have our ground, which we'll talk about the ground plane in just a moment. So basically you have to run 4 things down from this top module to the bottom one. And then they're also designed to sit in between switches, which we'll take a look at later on from this. But what I want to do first is kind of just break down the USB-C circuit first. So if we actually look at this, I'm going to right click and just ungroup this so I can select things a little bit easier. Basically how this works is we have our USB connector here, we have our ground from our resistors for the CC1 pin here and our CC2 pin here, just going into these 5.1K resistors. They're grounding out over on the shield because this would technically be shield on the USB port, but on my footprint is actually just ground, so that's what I was referring to. If I jump to my schematic here, you can see that we have our shield and our ground. If I select shield here and then jump over, you can see those are the shield. They're technically ground, so a little confusing there. Just think of them as ground. And then we have our V bus, which remember is 5 volt, so this is V bus. We're bringing it up here, and this is the first thing I wanted to talk about with routing in particular. You can see that I'm routing this on the actual front layer of the board, whereas I could have actually done this, where if I delete that, I could have routed this behind on the same layer as the pins, but when it comes to power with PCBs, you kind of want to keep power stuff away from any of your data lines. Now, I don't know how crucial it was that I routed it this way here. I just kind of wanted to keep it away from these as much as I can. So that's what I did as I routed on the back there, and it kind of keeps it clean because we have to pull the V-bus here out down to our fuse. So you can see we pull our V-bus from here, we pull it down into our fuse, it goes into the fuse, and then it becomes 5 volt over here. Now with that 5 volt, we're using this to power our ESD protection right here. We're also using that 5 volt to power our voltage regulator. And then also, if I jump up here, just kind of jumping around a little bit more here, we have our data lines. So you see we have our data minus here, data plus, so our 2 pairs of data lines. We're doing this like little fancy thing here. I did think about kind of routing it with these unnecessary vias. I just thought it might have looked cool if I kind of did that and did like that cross pattern, but I decided to not do that. So I just routed it like that. We connect the data minus to the other data minus. Same with this one here. We connect the data plus, and then we pull them down into our ESD protection. So they feed into here, and then they feed out straight down where we can connect them to the MCU later. Now, if we jump over here to the right, this is of course our voltage regulator. So we take our 5 volt in, we have our little stabilizing capacitor here, which is feeding to ground. You'll kind of notice this pattern too on all these. I'm using these vias on ground here. And the reason for that is we're actually using a ground plane to ground everything out. It's kind of a more standardized practice with PCBs. So if I actually zoom out here, I select my add a filled zone tool, and I just create a filled zone here. Let me select my copper layer so it will actually allow me. I will select both layers here. I'll go to ground, I'll click OK. I'll just make a selection around all this, and then I will press the B key. And you'll see that how this works is that these vias are basically tying the front and the back layer together. So if I select my back layer, you can see that this is now on the back layer. We also have the front layer. So both layers are kind of getting tied together. Now, did I actually fill this on both layers? I did not. Let me select that. I'll press B again. Then I can show this to you a little bit better. So you can see we have our front layer, that's all grounded out. The back layer is also all grounded out. And one thing that's actually pretty typical with PCBs when you're getting a little bit more advanced like this is to use what's known as a 4-layer board, whereas in the middle layer, so the middle, there'd be 2 layers here, 2 additional ones. They'd actually be completely solid, like filled copper zones. And that would help with things like EMI interference, which is if I come up here, let me just delete this filled zone really quick. It has to do with like this line here, this voltage line, like I said earlier, where you want to keep those away from any data stuff. If say I wanted to run my data line right like this next to it, there's the possibility that this voltage line creates EMI interference on this. Whereas if you had a 4-layer board, you'd have those 2 inner layers to kind of prevent that, where they would basically block all that possible EMI, electromagnetic interference, so you wouldn't have any issue. Now, where this can become a problem is say if you ran your reset button directly over some type of power line like this, it could actually reset your board if something triggered it. So it could be resetting your board randomly. You could get keystrokes randomly that you're not intending. So kind of when you're talking about like your matrix and your data lines, you want to keep them as far away as possible from any type of voltage line. So you can see that I'm routing my voltage as far away over here. And you can also see here that I'm pulling the voltage down and then I'm running it horizontal instead of parallel with the data line as much as I possibly can. And that's just because if this did run directly over here, you'd run that issue of possibly having problems there. Now, I think data lines, specifically data plus, data minus, I think it has something to do with the name impedance control. It does prevent this issue, but for like normal matrix lines or any of your reset stuff, you want to kind of keep it away from power there. But finally, if we just look at our power circuit over here again, you can see we grounded out on 1 pin. We have our 3V3 out. This is that stabilizing capacitor to stabilize that voltage. And then we feed that into our reset button here. So we have 3V3 on the reset button. We have our boot pin. This is supposed to connect to the boot pin over here. That is connecting to this, I believe, is this a resistor or a capacitor? If I double click that, it will tell me that is a resistor. That's just feeding to ground here. And then we have off of here, we can feed this down to our MCU. So before we actually connect this stuff to the MCU, I want to kind of run over what we have on the MCU here. So the MCU is super simple. We just have all our GPIO kind of exposed on the sides here. That was a consideration for this module I really took into account, is that I wanted the GPIO to be really easily accessible. So you can see pretty much every area on this, I keep them as easily accessible as possible so you can kind of get a lot of data lines out of this if I kind of start running those, you can see. But the moral of this here is that I want the left and right to be the primary GPIOs. So we have all these exposed on the side, and then these are all our decoupling capacitors. So you see if I right click, I just degroup this real quick. I can kind of start pinpointing this. We have our 3v3 pin here. That's feeding into a decoupling capacitor. We have our bulk decoupling right here. Same thing down here. We have another 3v3. We have a 3v3, all feeding into these 3v3 decoupling capacitors. Same down here, another one feeding in there. So this is a 3v3 pin. This is our end reset pin feeding into that. I believe it's a capacitor on this. Yes, it's a capacitor feeding right into the ground for that end reset. And this is what I talked about earlier with the F0 and F1. I actually kind of blocked those with the capacitor for the reset pin because, like I mentioned, you don't really want to use these unless you absolutely have to. So blocking those was kind of a consideration where it just kind of fit right there. Now, finally, we do have our last little decoupling right here up top. So those are the two modules. If I actually just regroup this really quick into the grouping right here, I'll group this. I will select this one up here and group it together. Where's my grouping button? Right there, group. What I'm gonna do here is I'm actually gonna press my A key to open up my add a footprint library because I wanna show you kind of how these fit between different components. Specifically, I made these to fit between two MX hot swap sockets. So if I just come in here and go down to my ScottoKeebs Scotto folder here, I can just have this MX hot swap 1U. I'm gonna select this and I'm gonna flip it onto the other side. I'm gonna simply copy and paste it here, grab this one, put a marker here, bring those together. I'm going to copy these, paste them, align them right here. What I can do is grab my USB module, and you'll see that it has this little alignment point here. So I'm going to put my origin right here, and then I'm going to grab this by that to move it with a reference, and then I can align that on the origin point. What you'll see is that everything nice and neatly fits between these two hot swap sockets. So if I actually open up my 3D viewer also, you'll be able to see that everything does fit between those. So that was the big point with these modules, is that I wanted them to fit between two hot swap sockets. Now this won't work if you're using, like, say, a column staggered board. It will work with ortholinear and row stagger. So pretty much any of those there, it should work because this is the minimum spacing of just 1U. So if you had like a 2.75 and a 1U, it should still fit between those. So if I just close down this 3D viewer here, you see that's the first module there. Now if I actually select these again, paste them down below, I'll align it right here. I'm gonna grab my MCU module. Yet again, it has an alignment point. We're gonna put the origin right on the middle there. We're gonna grab it by that alignment point. We'll pull this over here, and you'll see that yet again, this sits perfectly between those two hot swap sockets. So if we open up our 3D viewer, you'll see in here that yet again, everything nice and neatly fits between them. So now at this point, what we're ready to do is actually just wire up the 4 wires. We can come up top here, and the first one I like to do is kind of bring down these data minus and data plus lines. I will actually just click this. I'll open up my tool. I'm gonna right click and go to route differential pair. This is what I was talking about earlier in the schematic. So if I click here now, you'll see that these will route as a pair. So what I like to do is kind of bring them down, and I'm going to change my grid to something a little bit smaller. I'm going to kind of align them right there and then just pull them in finally like that. You could clean this up if you want to, but that's the basic routing for your data lines. You just kind of bring them into those pins right there. Now, the other one here is the 3v3 line. Now, this one I did talk briefly about earlier, how you want to be careful with voltage lines. So you wouldn't want to kind of bring this in like, you wouldn't want to do this with it, right? You wouldn't want that really close. Now, the other thing to consider in here is that voltage line should be a little bit thicker. So you can see that before we actually pull it from this pad, right here, it's actually a 0.3 millimeter trace, and then it becomes a 0.2. So I have this set up that we have different track widths up top here. So what I'm going to do is actually click this, and I just have a hotkey to kind of make it bigger. But that's a 0.3 line now. And what I'm going to do is pull this over. I'm going to put it here. I'm going to put a via, then I'm going to pull it on the other layer. I'm going to do that to jump over the hot swap socket. And then finally, it doesn't really matter where you put it here. I like to kind of route it into the capacitor here, and then that feeds the rest of it with voltage. So that's the rough idea of what I do for routing my voltage there, is kind of far away as possible from any data stuff. And the only one you're really jumping over here is the hot swap socket on there. Now, the final thing we have to route is our bootloader button. So this is pretty simple. I just kind of pull it down. I put a via to get it onto the back layer here because I don't want to interfere with these pins. So I'm pulling this on the back layer. I'll bring it underneath everything. I'll put another via to bring it onto the front layer, and then finally connect it in here. I did route these as a 0.3. These should technically be a 0.2, so I'm going to make them a little bit smaller there. You can see these are just 0.2 now, so everything on this should be routed properly. That's basically the overall idea of what you route here. Now, the final thing you want to do at the end of once you're done with designing your entire board, so we're just going to create a filled zone. So we're going to select everything here. We're going to select both layers. We're going to scroll down to make a ground fill zone, so we'll click OK. We'll just go like this, double click to close it, press the B key, and you will see that everything here gets connected to ground. So we have this grounding out here, grounds out really solidly. pretty much every via should ground everything out. And that's the overall idea of how this works for this schematic. If I actually jump into a 3D viewer, so you can see our traces coming down from here. These are our data lines running into the MCU. We have our voltage line kind of feeding off here. So this is 3v3, just feeding behind here. If I actually jump onto the other side, you see that's where it jumps. And then that feeds into the capacitor. And then we have, if I hide these, we can hide our actual components here. We have our bootloader button feeding down here into a via, flips onto the other side, runs down, flips back over right here. And then finally, it will feed into the reset button right here. So that is the overall idea of the PCB editor. What I'd like to do now is actually take a look at the physical PCB to kind of give you an idea of what this looks like on a real actual board. If we look up top, we have, of course, our USB-C port. We have our little 5.1K resistors here, which are for the USB specs. So remember CC1 and CC2. We have our resettable fuse right here. That's what the fuse looks like. We have our ESD protection chip down below. Of course, our big reset button right here. This is a pretty popular reset button. They're nice because they're really low profile. We have our voltage protection over here, and of course the stabilizing capacitor. So this is one stabilizing capacitor. This is 5 volt right here, and then this is the 3v3 one right here. So that's coming out as 3v3. And then finally we have over here just our resistor on our button for that, the spec for the button. Now if we look down below, we can see our traces feeding down. So these are of course our data lines in the middle here. This one will be our 3v3 voltage feeding into the pin right here. So on this one, I did feed it into the pin. Like I said, it doesn't really matter where you feed that because they're all so close here. As you can see, it doesn't matter if you feed it into the capacitor or the pin. Maybe technically there is a right reason to that, but this works on this from testing. And then we also do have our boot button feeding down somewhere, but it just goes behind the MCU here. And then of course, all these are our decoupling capacitors behind. So you can see that that entire thing kind of fits nice and neat behind there. Everything just kind of fits right between the switches. Looks really good. I kind of ripped that off there. But yeah, that's the overall board there. You can see that our USB port does stick out 0.25. I did have to do that to kind of get it to work. So if we look at it here, if I put this down lower, it wouldn't really work. So I had to kind of get it there. So that's just how I've aligned that. But that's the overall PCB. It's super simple. I think it's pretty easy to follow. Hopefully you guys could follow this. And also you can see that I have all my diodes on here too, because this was an assembled board. We'll take a look in a moment at actually assembling these on JLC, how that works. But the part of that is that you can get these diodes actually assembled on it. Now I will do a build stream on this eventually. This is a board that was sent to me by JLC. And something funny with this is that you can see here, I actually had to scratch off the pads because I messed up my footprint when I ordered it. So none of my hot swaps are able to actually be soldered on here. So that's just kind of one of my mistakes. I did fix that, so it's on the new version of this. It does have proper hot swaps, but that's the board. And what I'd actually like to do is take a look at this so you can kind of get an idea how that looks too in software. So we're going to jump into Kicad yet again, just take a quick look at this physical PCB on the Kicad software, see how that looks, and then we'll take a look at ordering them. So what I'm going to do first here is I'm actually just going to press Control B to unfill the zone. And you can see how this works is that we have our little module for the USB here. We have our MCU module. And then we just use those pins on the left and right to kind of route our matrix in. So we have our rows on the left here. So we have our bottom row, this row. They're all just kind of feeding into these pins. And then the same thing with all our columns. So we have all our columns. They kind of just feed down the middle here, and they feed into the pins on the left. And you can actually see that on the PCB here, that here they all are just kind of feeding in, same thing over here. So you can kind of put the PCB editor here to what the physical PCB looks like. Now, the one thing I do want to look at here too is I'm going to actually jump into the schematic. And this is where you can kind of see, if you haven't seen my last video, which I mentioned a few times in this video, you want to see my last video on Kicad stuff on how that works, is that we have our matrix up here. So this is the matrix that I've defined in a ton of videos, but we have all our pins. So all our B3, B4. It's just as simple as defining those on your MCU. So we have like B4 here. We have B4 up top here. So it's super simple to define everything, really easy to follow along. And I think it takes a lot of the guesswork out of these integrated MCUs. So what I'd like to do now is actually just show you, if we go into here, what you can do, of course, is just export using the fabrication toolkit. Yet again, this is something I mentioned on my last how to use Kicad video. But when you export this, everything will actually have the part numbers with it. So if I come in here and I go back to my schematic and I say go down to the controller here, or the actual MCU chip, and I double click this, you'll see that it has this LCSC number of the C81720, and then also this JLC rotation offset. So basically these define the part number you want to use and then what offset for the actual pick and place machine when they produce the PCB. So I can actually show you this part too. If I actually just copy this, and then I go to a browser here and I go to this part number, I'll just be able to search it. You'll see this pulls up LCSC, which is what JLC uses for their stuff. And you see that's the part. This chip here actually cost $1.2 per unit. And that's just kind of what those numbers are referring to. Yet again, if I actually jump over to the PCB again. I go back into the schematic here. We can select a different part. Say, let's just take a look at the X6206 here. Double click it. We'll have the part number here. We will copy that. And now that we're already on this LCSC, we can actually just paste this in here and it'll pull up that part yet again. You can see here's the part. So what we're going to do now is actually just upload this to JLC to kind of take a look at how that process goes, because there is some stuff you have to consider with these when you are ordering an assembled PCB. You could technically assemble these at home, but these parts, like I mentioned, I mean, you can see here, they are super tiny. So unless you have like a hot air machine or maybe a solder plate, you're not going to be doing this at home. So you're going to be using a service like JLC to actually get your PCB assembled. So let's just take a look at how that process goes. So here I am on JLC PCB. I'm just going to add the Gerber file for my ScottoLong PCB edition. After it does upload, you will get a preview of your board here, of course. And then what we want to select for this is we can leave all this the same. If it was a 4-layer board, like I was mentioning earlier, we'll automatically detect that. Pricing is relatively the same when you go to a 4-layer board, but technically that is a better design process to do if you are doing stuff like this, but it's not really needed for keyboards. It's not super crucial if you're careful with your routing. But basically, we're just going to use a 2-layer board here because it is a 2-layer. I like to select my PCBs as black. It kind of makes them look a little bit better. Everything else here is fine. You could go ENIG if you wanted to, which is gold. So you can get these to be gold pads. I don't ever do that because you can see it balloons the price here. I just do Hazel, so that's pretty fine here. And then finally, I always remove the order number. It is free now to do that on JLC. It's nice they finally did that. I also do confirm the production file. This is an option I always select because it basically allows you a second chance before they start to producing it to make sure that you actually upload the right file. So just like a double check here. Now, this is the important part for these PCBs, is the PCB assembly section. And typically there's like coupons on these depending on how you do it. But what we can do here is select this and you'll see that you have your different sides you want to assemble. I want to assemble the bottom side because you can see we have all our parts on the bottom here. And there's two different types of PCB assembly type. Economic is what this is set up to do. But if you wanted to also have the sockets soldered onto your board at the factory, you could define that part. And then it would also cost a little bit more. So if we select the standard here, you can see that our production cost for this is $25 now. Economic is $8. There's basically a setup cost for actually loading these machines. But I typically do economic because I don't solder the sockets onto the factory. And then what we can do is there's all these other options here. I pretty much leave those how they are. I don't really choose them. We just click confirm here, then we click next. And if you don't have an account, it's actually going to make you either create one or log in. I'm just going to log in here really quick. But this is what you'll see after you log in or create your account. It's basically just give you a preview of the side you're going to assemble. So you can see we're doing the bottom side. Everything's on the bottom here. We'll just click next again. And then you're going to want to add your bill of materials here, the BOM file and the CPL, which is basically for the pick and place machine. We're going to just click here and add the BOM file. You'll see that we have in our production folder, we have our production folder, we have our BOM, which is exported when you export your Gerbers. We'll just click that to open it. We'll add our CPL file, which is actually positions.csv here. We'll open that. We'll go process BOM and CPL. And then this is where it'll tell you how much everything costs for all your parts. So you can see we have our 100 NF capacitors here. It's going to cost us like 13 cents for those. These down below that says standard only, these are actually the sockets. I don't have those on this board because I didn't select the standard option for producing it. So when you go to click next here, what it's going to do is actually ask us to switch. I'm going to do not place this part because I don't want to place those. I'll click next again and then do not place. But with that now, the final thing on here is the actual layout of the board. This is where you can kind of get a preview of all the parts. So if we actually flip this over to the bottom, you can see here, it's a little touchy on the zoom here. The one part that never places right is a USB port. So what I always do is manually position this, but you can see everything else kind of positioned properly. We have like these little pink dots on these chips that have orientation that orients them right. So you're going to want to make sure that these are right in the way that it positions matches how your PCB is. But what I like to do for this port here is I actually flip to the top zone. I kind of try to zoom in as much as I can here. And I like to align it if I can kind of zoom in right without it freaking out, because it really doesn't like to move the way I want. We'll just zoom in there, and you can basically align this port with the holes right there. So you can kind of see how that works, is that these just align. I don't know if JLC will fix this or not. I assume they would if they see this as an issue, because it won't place it if it's like that, right? So what you want to do is just make sure that they're right on here. And then all you want to do next is just click next. And this will just give you a breakdown of what everything costs here. So you can see that we have our setup fee is $8. We have like our stencil fee. That's the actual stencil for the solder paste that they make. Extended components, because it does use some extended components. Basically, I have to manually load these into some machines. It's really no way around this, but that's the overall cost of what this is. And this is a really good time for me to actually talk about this, that I do not recommend jumping into integrated MCU boards like this if you don't fully understand what a keyboard matrix is and you're not comfortable saying that, okay, I know how this works, and you really understand how it works, because this is expensive. You can see that it costs $45 to get 5 of these produced. Now you're not factoring on top of that, it's about $40 for shipping. So it's about $80-90 to get 5 of these sent to you. So they're very expensive to get produced. And if you mess it up, you're going to have to do that again and again and again. And you just want to make sure going into this that you're really comfortable getting these made. But for this, it's not bad. I mean, this is what it is. It's $45 to get 5 of them produced. That's not terrible. Of course, this price will go down if you're going to get more or less of them produced. If you get like, say, 10 or 15, the price goes down per PCB. Just how economies of scale work like that. So hopefully that was easy to understand. I tried my best to kind of slow down, but whenever I do videos like this, I kind of get really talking fast. So if that was an issue, use the speed ramping option in the settings on YouTube down below. You can kind of use that to slow me down if you need to. But I also haven't mentioned either that these are kind of the bare minimum, right? These are the bare minimum working circuit for STM32. That's kind of the whole goal of the ScottoModules, to give you a bare minimum where you can plug in some GPIO pins and get a board working. But if you wanted to do, say, like I2C, you might need to do some additional work with pull-up resistors, or if you want to do like a split board, you might need V-bus sensing. That stuff's not implemented on this, so you'll have to kind of do some research on your own. But with all that, if you do know anything about PCB design and kind of have some stuff I could change here, let me know in the comments below, or just comment if you have something to say. Like the video as usual. Subscribe, of course, if you do like this content. It really does help. And I'll see you guys next time.